Hey, welcome to Areas of Plane Shapes. This is the first topic in the section called measurement. And I guess you're pretty happy looking at these figures about doing this topic now. Particularly, let's have a look at this one. This is a rectangle. You know a little bit about that, and you know a bit about areas. And it's over here, it's areas of plane shapes. So I wonder if you know about planes. Oh, I don't know. Oh, there's a plane. Cockpit up there. Uh-oh, I don't think so. Different type of plane here. What do we mean by plane shapes? Plane shapes means in the one flat surface or plane. We call a flat surface a plane. So let's just write that down, surface or plane. That's what we're talking about. It's flat. It's two-dimensional. It's come back over here to a rectangle, length and width. So I guess you say, hey, this is going to be good because I already know the area of a rectangle is length times breadth or width. Hey, that'll be good. What about these figures though? How would we find the area of these? And what we want to try and do is have a look at why the formulas work for each of these and really go to the next level in understanding about areas of plane shapes. So what I'd like you to do is to come down. I've got a little grid here for you, and we want to examine what area might mean. What do you think area means? Maybe a definition like the amount, I don't know, what do you reckon, amount of space contained within the figure? Would that do? Contained within the figure? Have you got another definition? You could have, there's quite a few of them, but that's a fairly basic common sense one. The amount of space, what space though? Rockets, no, not outer space, man, just space. Oh, well, how do we measure space? I guess you already know. We have a look at how many squares, it's 1 centimetre by 1 centimetre, or let's say 1 metre, this is not the scale of course, 100 centimetres in a metre, 1 metre by 1 metre, or 1 kilometre by 1 kilometre. How many of those dudes would fit in our particular shape? That would be a measure of space. And of course, what we say there is that it's centimetres squared, or metres squared, or kilometres squared, whatever the size of the figure that we want to be measuring. All right, well, let's have a look at this one over here now. And I'm going to start to draw in, there's one. These are all centimetre by centimetre. I'm counting these up. Hey, hang on. This is going to take me a while. Is there a quicker method than just counting up all the squares in there? Well, let's have a look down here. Let's measure this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So there are 12 centimetres going down there. And we've only come across one. We've come across a distance of 1 there. So we've got 12 centimetres. But hang on, let's see if we can do it by a quickie method here. Across here, how many have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 centimetres. What are we going to do with this? Well, I want to show you a little way of doing quick addition. What do you know about addition? Addition. Okay, addition is adding them all up, isn't it? So that's like adding up all the squares in here. Is there a quick way of doing it? Let's do, let's say, many additions. Multiple additions. How do you do multiple additions? Uh-oh, do you realise that's what multiplication means? Multiple additions, multiplication. So when we say we have, let's say, there's a bundle of 2, there's another bundle of 2, and another bundle of 2, oops, then we've got 3 lots of 2. And multiplication, 3 times 2 instead of lots of, is our mathematical way of getting the total 6, rather than add up. 2 plus 2 plus 2 is 6. Do you get it? Have you seen that before? That really, multiplication is multiple additions. Have you thought about that? Okay, anyway, let's use that now in our figure here, because what have we got? Well, we've got a row or a column of 12. But, hang on, we're going to do that. I'm going to write this slightly differently. Across here, we've got 15 lots of them. We've been 15 lots of columns, all equal to 12. 15 of them. So how many? The total number. Let's do a multiple addition. The total number is 15 lots of 12. Okay, you might forget the calculator, but I think that comes to 180. So we've got 180 centimetre squares in there. 180. Now, are you thinking that's where the area formula, length times width, comes from? Isn't it? That's what we're doing. But do you see it? Have you taken it to that top level of understanding? Let's do it differently now. Let's scrub that all out and do it in general. So what we'll do is we'll put dashes in here. We'll say that we don't know how long this really is. This is the length and this is the width. We'll just put dashes. So what this means is we've got L along here in this row, in these rows, and W up here. So we don't know what these are. Dot, 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 dot. There's W of them, and there's L along here. What will we do to do our multiple additions? Well, our area, our total number of squares, is L lots of W, whatever L and W are. So that means A equals L times W. That would be our general simple derivation, if you like, of that formula. That's why it works. We are doing multiple additions down here, multiplication. Do you get it? Because what I want you to do in this little unit is to take it to the next level. Things that you've learned off parrot fashion or by rote in the past. I want you to think if you could actually prove that those formulas work. Okay, come on down and let's have a look at our next little pair here. Okay. Well, here we go. We've got our rectangle. Now we've already just looked at that one. Okay, length times width. So I think we're okay with that. What about a triangle though? What about a triangle? You know, I guess, area is a half base times height. But I wonder why that works. Let's try it together. You might like to pause the presentation and see if you can make a connection between the triangle and the rectangle. Because it looks like there's some connection here, and I'll give you a hint. Something like that. All right, pause the presentation, have a go. I'm going to go on now. Let's complete a rectangle here. Make that one there a rectangle. So what will that be? That'll be H across there. And let's complete this rectangle here out to there. So what have we got now? If we complete this here, then these two will be the same. And if we complete the rectangle over here, these two will be the same. Okay, so the diagonals rectangle bisect the figure. Little bit of deductive geometry that we're doing later on, Euclidean theorems and so on. Okay, so what have we got? Well, let's take the whole green triangle now. Green rectangle, sorry, we've made it up like that. Now it's H and B, so the area of that is length times width from over here, from before. We're building, once we've established that one we can build on it. So, and we've got to half that. So the area of the triangle is a half that, because we, by symmetry, have said this one and this one are the same, this one and this one are the same. So we've actually got the area of a triangle as a half base times height. That's the level I want you to go to. Let's go on and do some more now. Okay. Parallelogram and a trapezium. Do you want to pause the presentation and see if you can work these out? Now, we're not going to do them all here. You might like to come back or work with your teacher on that. But pause it now and have a go maybe at the parallelogram. All right, let's have a look at the parallelogram now. What I might like to get you to do now is to think about, I don't know, what's the best way of doing this? Maybe drawing a perpendicular down there, cutting that out and putting it over here. So, if you do that, this will complete a rectangle in there. And what do you notice about the green rectangle? Area of the rectangle is length times width, which if we put this over here exactly, then that will become still the length B. Length times, and this here will be the height stolen from in there, B times H. So the parallelogram can be thought of as forming the same area as this equivalent green rectangle in here. Okay. Do you want to do some more? Well, you can do this, the trapezium one, in a couple of different ways. You can actually start building in here and look at doing it like that from an overall big rectangle and take away pieces, or you can build inside here. This is a little bit longer algebraically because they got B's and A's and things added up there. So the important thing here is you might have to work through that a little bit. Okay, so let's have a look then at some of the others now. Okay, so you might like to work on that one. Let's come down and have a look here at our circle and sector. Now, unfortunately, with the circle, I think you've probably seen this. Area is pi r squared. Now, you actually have to use calculus, and now you won't see that until year 12 to prove the area of a circle is pi r squared. You can see the difficulty. You can't actually fit squares in here very easily. There's a part of a square just in there and so on because of the curved line. There is a way of doing that. Now let's have a look at the sector. A sector is a piece of pie like that, and again, it's hard to see how you'll get exact squares in, but little halves add up to others to give whole squares. So how would you work it out? Well, let's have a look at the formula and see if we can understand it. This is the area of a circle. The area of a circle. What's this doing then? Can you see it? You've got theta out of 360. Theta 360th. So if theta was 60 degrees in there, you would have a sixth of the circle, and therefore a sixth of the area. So theta over 360 is the fraction of a whole circle that you've got. Because if you had 360 degrees, that's the whole angle at the centre. You've only got, let's say, 60 out of 360, so you've got a sixth of the whole circle's width, and therefore you've got a sixth of its area. So that's a new one for you, I think. But again, can you come back, where possible, and say, can I see it? Can I see what's going on? Now this one over here, the area of a circle, is too hard. You haven't got enough mass behind you yet to do that one. But we'll use the formula because it's handy. And it leads us on to be able to do the sector as well. Come on down, let's do some more. These two are a bit more unusual. And again, you could play with this. A rhombus, remember, is a square pushed out of shape, if you like, or a parallelogram with equal sides. So they are all equal. These two opposite sides are parallel, and they put it up this way. The area of that is a half, if you like, the product of the two diagonal lengths there. You can see here x is the distance that way and y is the distance that way. And similarly with the kite, you take its overall dimensions and it's a half the product of the two. You have to do a bit of work to prove those. You might have a look at those a bit later on. Let's go on now and have a look at how we can use all this stuff. Well, first of all, we've seen the plane shapes, but what we want to do now is have a look at composite figures. Composite figures. They're composed of various basic shapes. Let's have a look at this one over here. We see a rectangle, a triangle, a rectangle, and a semicircle. Now, composite figures can be handled in two ways. I'm going to call this A1, A2 and A3. And probably the best way of doing this one is the area is the sum of these three added up. And then just go and do it. Do a triangle, a rectangle and a semicircle, half circle. Alright, what's another way of doing it? Well, this one over here is probably better done the other way. And that's to say, well, I want the shaded areas and they aren't commonplace figures. They're not common figures. So I'm going to say the area I want is the big area. Now, what's the big area? It's a semicircle. Okay, so let's call this A1, the big area, and I'm going to take away in here, let's go and remove that now. I'm going to take away the triangle, call that A2. So you can do it by difference. Got to be a little bit tricky here. What is easier, to take away from a known area, another known area, or to build by the sum of known areas? So there's two different approaches to composite figures. And that's what we're going to build on this year. That's going to be the newest part of this unit, because you've seen a lot of it before. What about these? Now, these can be done in either way. They are composite figures. But you might, let's look at this one here. You might look at it by method one if you like. It's A1 plus A2. Oh, well, that's okay. But hang on, we could do it differently. We could call the big area, completing this, as A1, and take away this little dude in here, A2. Couldn't we? Ah, that's interesting. What about this one over here? Well, let's do it by the first method. That would be a rectangle, another rectangle, another rectangle. So we could have A1 plus A2 plus A3 plus A4. Oh, all right. Well, what's another way? We could have the big E, take a big rectangle like that, call the whole thing A1, and then take away this bit in here, which is A2, let's say, and A3, which would be a rectangle and a triangle in there. We'd be trying to work all those out. Okay, so stay flexible. Which way, which method do you want to choose, and what's the answer? What is the best mathematical solution to a problem? And the answer to that is the shortest method. That will always be the case in mathematical solutions. The best solution is the shortest method. Let's do some, shall we? Let's come down and have a look. I'm using Pearson's textbook here for the new national curriculum. And so here we're going to start with a composite figure, the one that I just gave you there. So let's split it up. We've split it up into 3 known shapes. Not a bad idea to draw them. This line, however, is extremely important. So if you don't want to draw it, you could put A equals area of the triangle plus area of the rectangle plus area of the semicircle. You could write it. It's always a good idea to do that. And then put down the formula for each part. Area of triangle, half base times height. Area of a rectangle, length times width. Area of semicircle, half pi r squared. And you don't have to put, you wouldn't generally put all that working in there, but you put it on your figure generally. So here, what they're saying is, if you've got 4 there, then how long is that bit in there? That's 14. Okay, that's the idea. And then, if this is 6 centimetres, the radius of this will be 3 centimetres. So this is working out, probably best done on the diagram. Mark it on the diagram. Or if you're going to work it out like this, put it across on the right-hand side, working column. So you have to do a bit of sussing out here, this sort of thing here. If it's 18 from there to there, take off 4, that length of that rectangle in there is 14. Can you see it? Okay, so then you do the separate substitution in here. Base times height, then length times width, and then a half pi r squared. It's a half pi r squared because it's half a circle. And then we can add those up and leave it in pi. And it depends. It says up here, right at the top here, 2 decimal places, so you'll leave it like that. If it doesn't say, then you can leave your answer as an exact form or to 3 significant figures is a general way. Alright, do you get it? Let's go and do some more. Here's another little dude down here. This is the other one I was showing you. So this is probably better done by the other method now, and that's to say do the big shape and minus the other one. So here we are. This is the triangle that you might be working with. These are both equal, so you need to do some work here to get some more numbers. You've got the square on the hypotenuse is the sum of the squares on the other 2 sides, and they're equal. Usually you put Pythag in brackets, and so 2x squared equals 13 squared. X squared is 13 squared on 2, or square root of 84.5. It's not a bad idea to leave it like that. So that you don't round off too early. You don't want to round everything off, you lose accuracy as you go. So keep it as exact as possible as you go through there. Now, the shaded area is going to be this, the big one, a half pi r squared, minus this triangle here, which is a half base times height. It's the whole base now. What did we do? This was only half the base, wasn't it? So here we've got it. Base equals here 2 times this value, or twice what we had before. So it's a half pi r squared minus a half by 2h by h. Well, I think we would probably go down to this line here. I don't think rearranging this algebraically is a good idea. So this is a half pi, let's come down, r squared, that's alright, but here you probably have, what did we say here? Let's put in the numbers. It's a half the base and the base was 2 times x from before. So 2 times root 84.5 times the height was another x, remember, up here. So maybe put in numberland rather than rearrange the formula. Okay, just put in the numbers that you've found for the various pieces. Just watching here, this is typical of mathematics, sequential and cumulative. This is old knowledge. This is a problem. You need to build up your skills and accumulate them, and accumulate knowledge. You need Pythagoras in this one. Okay, so, and then you can do it all in pies. Probably we wouldn't do this, we'd put on the calculator and then round it to 2 decimal places, because that's what they asked for. But the important thing is, do not truncate or round off only for the final answer, because you're losing accuracy every time you truncate a decimal or round off. So keep as many figures as possible. That's why up here, come up here, that's why they have not found the root of 84.5. Now you can, but don't truncate it. Use all the decimal places and use select answer on your calculator to go on further. All right, let's go on and have a look. Here's an interesting shape, the area of an annulus. An annulus is a ring shape. So it's a shaded area here. This is the annulus. And there's some interesting maths here. You might do this in gardening or something like that. We haven't actually talked about why you would use area. If you're a painter, you'd use the area of a wall, wouldn't you? If you're trying to work out how many litres of paint to cover 20 square metres or something like that. You have to know the area you're working with. Well, what would the area of an annulus be? Well, this is typical of a big circle minus a little one, isn't it? A big radius minus the one inside will give you the gap in between. Now, if we had this, let's say that R was something like 20 centimetres, big R, and little r was, what's it look like? Oh, it's about half, isn't it? 10 centimetres, something like that. Okay, we'll come over here. Here's the formula. A is pi big R squared minus pi little r squared. Oh, the numbers are getting big. 400 pi minus 100, oops, left out pi, minus 100 pi is 300 pi. Now, if you're squaring numbers, and they might be decimals, that might be a little bit inconvenient. Look at what we've done over here with some maths. Taken pi r as a common factor and said the difference of two squares. Here it is here. R squared take R squared. A squared take B squared. Remember that? A squared take B squared is A plus B by A take B. Now this is useful here. You watch it over here, because I'm going to put or. If I used R plus R take R, instead of squaring big numbers out, I would have R plus R is 30 and R take R is 10, and I get 300 pi. Now that might be a bit easier rather than have these big squares up here. So there's a little bit of algebra to the rescue there. Algebra can actually, using this, help you simplify some practical working out. I mean, most people think that algebra is fairly theoretical and used in problem solving, but here it can be used to simplify a calculation. All right, so keep that in mind, particularly where these squares might involve decimals. It gets a bit messy even with a calculator. Okay, want to have a go? Well, let's have a look now, and here are the problems. And I've got the answers down the right hand side here. So what I want you to do is to have a look at most of these, particularly more difficult ones, some of these fancy shapes here and here. And you do most of those, just cruise through. So there's question 1. There's question 2 and 3. We'll just pause the presentation and have a go. Remember which way to select your composite function area. Are you going to sum two known areas or take them away? So you think about each of these, maybe do some one way, some the others. You won't be able to do all of them both ways though. Question 3. Best way of doing multiple choice is to actually work the problems out. Okay, or to recognise, try to work out what those areas are there. All right, let's go down to the next level, the understanding questions. So there's question 5. And you have to pause the presentation, have a go at some of those hard ones there. And question 6, and well, we can get up to 10, can we? No, we'll just go there. Question 6. Have a go at some of those. You won't have time probably to do all of them, but challenge yourself a little bit with these harder ones, particularly with the worded ones that don't have a diagram. They get hard. Let's go down to question 10. Okay, that's an interesting one. And in the reasoning ones, 11 through 13. All right, and then in the last one, question 14, the open-ended ones, 14 and 15. Okay, just drop it down a little bit to there, something like that. Okay, so those open-ended ones, of course, you can have many answers to them, and there's just a sample answers over here. All right, I hope you enjoy yourself. This is a good practical fun now, so work hard on it, and I'll catch you in the next section in the area called measurement. Cheers for now.